Alrighty, I'm Dale Southard from NVIDIA. I'm going to cover our recent accelerator roadmap and some of our hardware and software. So a little bit of motherhood and apple pie. GPU computing has been on the rise in the last 10 years, really because, as you've heard, Moore's Law hasn't died, but what Moore's Law gives us is more transistors, not necessarily more single-thread performance. So single-thread performance has been flattening for the last decade or so. GPUs are getting about 1.5x performance a year, and that's not because we're going faster on an individual core basis, but we're a more efficient way to add a lot more cores in a constrained silicon environment. And of course, then at the system level, by scaling our interconnects, we're able to scale beyond Moore's Law. So if you look at 2013, 5 years ago, an accelerated server with Fermi compared to an accelerated server with Volta today. And we're getting, again, better than Moore's Law, better than straight latency optimized core performance. NVIDIA's CUDA and our GPU is the most adopted HPC and deep learning platform in the world. Looking back 6 years, our downloads are up about 8x. We've peaked over 500 applications that are now accelerated with CUDA and GPUs. The top 15 HPC applications are all accelerated or have acceleration in progress. And we've got already the fastest supercomputer in Europe, and this year should have the fastest supercomputer in Japan and the US as well. And all of this is because in addition to making good hardware, we actually make a complete stack. So we're not just providing you guys with GPUs, a C compiler, and an instruction manual and saying, go forth and program. We actually work extensively up and down the stack, both on the hardware level in terms of GPUs as well as platforms, and then up through libraries, frameworks, and full application acceleration. So we're really involved at all layers of the stack. And because of that, we're able to provide an end-to-end product family. So in areas like automotive, we can provide a module for safety and assisted driving that includes not just the hardware, but the software, and in some cases, the backing data to help companies accomplish what they need to. And of course, on the deep learning and on the HPC side, we've also started to venture into system design. We have both our DGX1 and our DGX2 that I'll talk about that we've released in the last year to address some of the needs in those markets where they need a vehicle to introduce technologies quickly. So now that I've gotten the marketing gack mostly out of the way, I will talk about GPU computing for HPC. So NVIDIA strongly believes that HPC and DL are converging. That's not to say that HPC developers are going to be replaced by kind of tattooed hippie-looking guys with piercings and stuff that are just going to deep learning their way out of stuff, but that as a technique for solving scientific problems, deep learning and inference are going to provide important acceleration in the same way that Fourier transform and iterative solvers and other techniques provide important ways to solve scientific problems. So I've got a few slides here, or examples here on areas where they've introduced deep learning. I've got a lot of other examples if somebody wants to track me down afterwards when I'm not watching the clock. Tick, tick, tick. Because of this belief that deep learning and HPC are converging, NVIDIA focuses all our energy on one platform that's amenable to both traditional modeling and simulation science, as well as big data and deep learning science. So we're not bifurcating into GPUs for doing chemistry and another GPU for doing Google search. We put all of our energy into building a single platform that works for all of the computationally intensive needs, whether they be HPC or DL. And to that end, we announced at GTC a few weeks ago the latest accelerator, the Tesla V100 32 gigabyte. This is based on the Volta architecture. For those of you familiar with Volta, the specs have not changed, so it's the same number of CUDA cores and tensor cores. Everybody understands what I mean when I say tensor core? No? No? Okay. So we have both our traditional FMA cores that are floating multipoint add that work in 16-bit, 32-bit, and 64-bit floating point precisions. But with the V100, we also added 640 new tensor cores that work with tensors. And the result of that is, if you're looking at flops, you can see from for traditional mod sim and double precision, you're at 7.8 flops. In 32-bit precision, you're at almost 16 flops. And then there's this huge jump for tensor flops. And tensor flops are, in essence, 16-bit precision accumulating into 32-bit precision, which so happens to be an important operation in a lot of deep learning, especially for training. So we're able to, with one chip, to provide over 100 teraflops of deep learning training. The other things are the same. The thing that has changed is we've gone from 16 to 32 gigs for this product because we had a lot of areas where 16 gigs wasn't sufficient or they wanted more. Other than that, the product's the same. We still sell the 16 gigabyte version. Whether you use this large or small memory is just a question of what your workload is anticipated to be. They're the same board in terms of form factor. They use the same cooling solution. They just use a different stack height in the HBM. So I said one platform built for both computational science, and I'm going backwards there. So with this 32-bit, we've seen some fairly impressive performance gains in a couple areas. These are all DL. I'm sorry, there should be one RN. So we've seen it in both DL and HPC. And again, it just depends on what your data size is. If you had data that was not quite fitting into 16 gig, moving to 32 gig provides a pretty big performance improvement when you're accessing that data at 900 and some gigabytes per second. And the result of that is it saves you money. It gives you more science for your dollar. So on the left is a self-hosted set of self-hosted Skylake servers running a mixed HPC workload of what I've got there. And then here is the same workload running on 8 accelerated servers, each of which have 4 V100 GPUs. So you can see we can run the same workload in less cost, less space, less power. The other thing we announced at GTC was NVSWITCH. So you heard the IBM talk discuss NVLink and NVLink 2.0. What NVSWITch is essentially a crossbar for NVLink traffic. So what we've used NVSWITch for is a series of NVSwitches to combine 16 GPUs into, in essence, one large GPU. So we use NVSWITch to extend the memory systems of all the GPUs. They can now load store directly into each other's stacked memory spaces. We've got a fully non-blocking fat tree between all of them. And with that, we can provide 512 gigabytes of stacked memory space to a single application running across these 16 GPUs with NVLink between them. We incorporated that into a server we're calling DGX2. It's quite large. It weighs about 380 pounds. I'd suggest not dropping it on your toe while moving it. It's, as far as we can tell, the world's first 2 petaflop single system. So we can provide 2 petaflops of deep learning training in a single box running 1 operating system. And again, we're seeing higher performance. This is comparing a pair of DGX-1s, each of which has 8 GPUs, and then connecting those with 4 InfiniBand connections, versus a single DGX-2 with 16 GPUs. So it's 16 GPUs against 16 GPUs, but the difference is the interconnect used to join them together. In the gray bar case, you have groups of 8 connected by NVLink in a non-fully connected topology, and then those connected by 4 rails of InfiniBand, and on the right you have the fully connected fat tree in DGX2. As you can see, in both traditional kind of physics and weather, as well as in deep learning, we're seeing fairly good performance improvement, even though the GPUs and the number of GPUs hasn't changed. So computationally, we have about the same amount of flops here. In fact, there's probably more flops on the left, because the left has 4 CPUs, and on the green bar there's only 2 CPUs driving all 16 GPUs. But we're getting better throughput anyway, and that's again because we're taking the resources we have and more strongly connecting them. And with that, I'm actually kind of done here, but I have 2 minutes, so unless somebody shouts me down, I'm going to talk just quickly about the GPU cloud, since it came up in an earlier talk. So NVIDIA has a GPU cloud. You can think of it as a registry of containerized applications. It works on NVIDIA's GPU cloud, as well as in Amazon and Azure, in other cloud providers. Essentially, you can log into the GPU cloud, pull down a containerized image, and just start running your app on the GPU with no compilation. Initially, that was just for deep learning apps, but what we've added over the last 6 months has been HPC apps. So we started with games, GROMACS, LAMPS, NAMD, and Relion, and we've since added Candle, Chroma, Milk, and some Lattice Microbes containers. We'll slowly add more containers as we have time. You can expect 5 or 6 a quarter moving forward as we get apps that people ask to be containerized. We also containerized the visualization apps. So we've started with ParaView with different backends that utilize the GPUs. And we've now added VMD, which is a molecular dynamics visualization package, as well as Index, which is a volume rendering package. Again, all these are containerized. If you're on the NVIDIA GPU cloud, you can just pull them down directly into your Amazon instance or into a DGX on-prem and start computing. So with that, now I will stop talking.